Welcome back. Here's today's challenge. We want to find every value of k that satisfies the equation k squared minus k cubed equals 12. At first glance, this doesn't look especially inviting. There's a cubic term, a quadratic term, and a constant, all competing for our attention. But before we touch the algebra, let's do what mathematicians do first. Pause for a moment. The highest power of k is 3. That means we're working with a cubic equation. And that's useful because every cubic has 3 solutions, altogether when complex numbers are included. So our mission is already clear. We're not just looking for one answer, we're looking for every answer. Now the next question is just as important. How should we begin? Could we take cube roots? Not really. The k squared term gets in the way. Could we factor immediately? Not yet, because nothing obvious jumps out. So the most natural first step is much simpler. Let's move everything to one side so the equation equals 0. That changes our equation into k squared minus k cubed minus 12 equals 0. Why is that helpful? Because once a polynomial equals 0, we unlock some very powerful algebraic tools. There's one more tiny improvement we can make. The leading term is negative. That's perfectly correct, but mathematicians usually prefer a positive leading coefficient because it's easier to read and easier to analyze. So let's multiply every term by -1. Since we're multiplying both sides equally, the solutions don't change. Now we have k cubed minus k squared plus 12 equals 0. Much cleaner. Now comes an important decision. Whenever you see a polynomial with whole number coefficients, it's worth asking one simple question. Could it have a rational root? The Rational Root Theorem gives us a short list: positive or -1, 2, 3, 4, 6, and 12. That's actually a pretty short list. A little testing might save us a lot of work. Let's start with the simplest candidate. Suppose k equals 1. Substituting gives 1 cubed minus 1 squared plus 12. That's 1 minus 1 plus 12, which equals 12. Not 0. So 1 isn't our solution. No breakthrough yet, but that's perfectly normal. Mathematics often rewards patience. Let's try another candidate. This time, let k equal -2. Substituting gives -2 cubed minus -2 squared plus 12. -2 cubed is -8. -2 squared is 4. So we have -8 minus 4 plus 12. And that equals 0. There it is, our first real breakthrough. -2 is a genuine solution. Now here's the beautiful part. Whenever a value makes a polynomial equal 0, the factor theorem tells us that the corresponding linear expression must be a factor. Since -2 is a root, k plus 2 divides the polynomial exactly. We've just transformed the problem. Instead of searching blindly, we now know one factor with complete certainty. The only question left is, what's the remaining factor? To find it, we'll use synthetic division. Watch the pattern carefully. Bring down the 1. Multiply by -2 gives -2. Add -1 and -2 gives -3. Repeat. Multiply by -2 gives 6. Add 0 plus 6 gives 6. Repeat. Multiply by -2 gives -12. Add 12 and -12, which gives 0. Exactly what we hoped for. The quotient is k squared minus 3k plus 6. So the original cubic factors beautifully into k plus 2 multiplied by k squared minus 3k plus 6. This is the turning point of the entire problem. We've reduced one difficult cubic into two much simpler equations. Either k plus 2 equals 0, or k squared minus 3k plus 6 equals 0. Let's solve the first one. Subtract 2 from both sides, and immediately k equals -2. Our first solution is safely confirmed. But remember, a cubic has 3 solutions altogether. We've only found one. The quadratic still has 2 more stories to tell. Can you guess what kind of solutions they're going to be? Let's find out. We now solve k squared minus 3k plus 6 equals 0. Can it be factored nicely? A quick check says no. So instead of forcing a factorization that isn't there, we'll use the quadratic formula. Exactly what it was designed for. Substituting the coefficients gives k equals 3 plus or minus the square root of -3 squared minus 4 times 1 times 6, all divided by 2. Can you predict what's about to happen? Let's simplify the discriminant. -3 squared is 9. 4 times 1 times 6 is 24. So 9 minus 24 equals -15. And that tells us something important. Because the discriminant is negative, there are no more real solutions. Instead, the remaining 2 solutions are complex. Using the imaginary unit, the square root of -15 becomes I root 15. So our final 2 solutions are 3 plus I root 15 divided by 2, and 3 minus I root 15 divided by 2. Notice how they arrive as a pair, one with a plus, one with a minus. These are called complex conjugates, and whenever a polynomial has real coefficients, they often appear together. Let's collect everything. Our first solution, -2. Our second, 3 plus I root 15 over 2. Our third, 3 minus I root 15 over 2. 3 solutions altogether. Exactly what we expected. But good mathematics doesn't stop when the answers appear. It verifies them. Substituting -2 back into the original equation gives 4 minus -8, which equals 12. A perfect match. As for the complex solutions, there's no need for messy substitution. They came directly from solving the quadratic factor. Since that factor came from an exact factorization, every solution automatically satisfies the original equation. That's one of the rewards of careful algebra. Now let's step back. The highest power of our polynomial is 3. The Fundamental Theorem of Algebra guarantees exactly 3 complex solutions, counting multiplicity. We've found 1 real solution and 2 complex solutions. Nothing is missing. Nothing is left to discover. Before we finish, here's one more beautiful insight. Instead of beginning with algebra, we could have graphed y equals k squared minus k cubed together with the horizontal line y equals 12. The graph would reveal only one real point of intersection. That hints there's only one real solution. The algebra then uncovers the 2 complex solutions, hidden beyond the real coordinate plane. A wonderful reminder that algebra and geometry often tell the same story, just from different perspectives. Now here's your challenge. Try solving x cubed minus 4x squared plus 4x minus 16 equals 0. Start by looking for a rational root. Then factor the polynomial. Finally, solve whatever remains. Pause the video and see how far you can get before checking your work. Remember, mathematics isn't about memorizing tricks. It's about discovering patterns. Today, we didn't just solve a cubic equation. We learned how to choose a strategy, justify every step, and understand why the solution had to be true. Keep exploring, keep asking why, and I'll see you in the next lesson.